All right, everyone. So now we're going to talk about reagents in acid-base reactions. And one way to think about this section is it's more like sort of practical considerations that you have if you're trying to carry out these types of reactions. So for example, oftentimes we'll have a particular molecule and our question is, well, how do we go about protonating that molecule? What choice of acid or base do I need to actually accomplish a protonation of? In this case, we're going to do this target molecule here, which is an acetylide ion. And so let's sort of pick apart how we would go about doing that. Okay, so again, we're going to try to protonate this molecule here. So what are we going to use to protonate this molecule? An acid or a base? So here's where terminology is really important. What does protonate mean? It means give a proton to. So what are we going to use that's going to give a proton to this molecule? That would be an acid of sorts, right? So we're going to need to find an acid. I'm going to use the generic form of an acid here, HA, and then we'll plug it in with a real molecule. But this plus our acetylide ion, there's going to be an acid-base reaction here. So then I'm going to have to figure out what my products are, right? So I need to figure out what the conjugate acid and conjugate base is. Well, the conjugate base of my generic acid here is just A minus, right? Remember the minus because it lost a proton. And then what's my conjugate acid? That's just going to be acetylide. I mean, I guess to be clear, let's do this. There's a hydrogen here now that was originally for my proton. There's actually a hydrogen over here too, so I don't want to be confusing, but yeah, I want to indicate which one actually came from the acid. Okay, and we need this, most importantly about this reaction is we need it to proceed in the forward direction towards the products, right? If I mix it with some acid and it favors the reactants, that doesn't really do much for me. So the real question is what acid can we choose? Which replacement for this generic HA can we choose that will actually push this reaction forward? So what we got to do is look at pKa's. We're going to have a pKa associated with this acid. Right now it's a generic acid, so we don't know what that is, of course. And then we're going to have a pKa associated with our conjugate acid as well. So that would be this guy over here. The pKa of acetylene, right, the protonated form, is, oh gosh, I want to say, yeah, 25. I guess I can just get rid of this. So the pKa, right, I just looked this up on my table, is 25 for this. So if I want this reaction to proceed in this forward direction, what acid am I going to choose to create that? So obviously, if we look at our pKa table, we can just choose the strongest acid on there, right? Hydroiodic acid or something ridiculously strong. Okay, but that's kind of cheating. What we really want to do is figure out what's the weakest acid that we can use, right? I mean, we can always just toss the strongest acid we can think of in there, but what's the weakest acid that we can use to accomplish this? So remember, in terms of your pKa's and in forward reaction, what's the relationship between the pKa of the acid? I guess let me just be really good and label these here. My acid here, this is playing the role of the base. This is my conjugate base. And this is my conjugate acid. Conjugate acid. All right, so what's the relationship between the pKa of my acid and my conjugate acid that I'm looking for if I want this reaction to proceed in the forward direction? That means that the pKa of my acid has to be less than 25, right? That will guarantee that that reaction proceeds in the forward direction. So any acid from that table with a pKa less than 25 will successfully protonate this in the forward direction. Okay, so if I'm asking you for the minimum, for the weakest acid that I can use to do it, in this case, it's going to be just going from the table here, CH3C. And then there's, so I guess I'm gonna go ahead and use our bond line structures. Okay, and specifically referring to this proton here, Hopefully you guys, I mean, just as a practice, hopefully you can tell me what that functional group is. That's an ester. So you see that the hydrogen adjacent to that carbonyl carbon in an ester is slightly acidic, and in fact more acidic than the conjugate acid of acetylene. Nice, okay. But that's sort of how we would go about picking a reagent. Again, we could always just choose the strongest acid, but that kind of defeats the purpose of the exercise. So now we can do the flip side, right? So now here, I need to find find a molecule that will effectively deprotonate the following. So this is, right, our hydronium ion, or H3O+. So the question here, so first of all, if I'm trying to deprotonate this, am I going to choose an acid or a base? So it should be a base, right? Because bases deprotonate. So here I'm looking for H3O plus some base. This is something I want to point out. This right here represents a generic base. You will actually often see it with 2 dots right there because all bases have lone pairs. It is not boron, okay? 99.9% of the time when you see a random B in an organic chemistry reaction, it means generic base, meaning we don't really care what the base is as long as there's a base there. This is something that you'll see over and over again. It never means boron unless it's like BH3 or BF3 or something like that. So just something that you should kind of prepare yourself to get used to. But yes, so this is my generic base here. I'm then going to have on the other side of my equilibrium, I'm going to have the conjugate acid and the conjugate base. So the conjugate acid of my generic base is Hb+. Remember, when I add that proton, that formal charge has to go up. And then the conjugate, did I mess that up? This is the conjugate acid. Conjugate acid of my base. I feel like I might have messed that up, but whatever. We're going to move on. All right, and then my conjugate base is just water in this case. Okay, here's my base. Here's my acid. And again, the whole point of this problem right here is I need this reaction to proceed in the forward direction. I'm going to choose a base specifically so that it proceeds in the forward direction. There's no point in choosing a base where, you know, I mix these two together and it basically just all stays reactive. It's not going to help anybody. So then I'm going to look at pKa's. Again, the whole idea is to choose pKa's to choose compounds such that, you know, when we look up our pKa's, they show that there's a forward reaction. So first of all, the pKa of the hydronium ion is -1.7, super low. So this is a super acidic compound. So then I'm going to look up the pKa of my conjugate acid. What should be the relationship between the pKa of the conjugate acid and the acid if I want the reaction to proceed forward? Right, so this is going to have to be greater than -1.7. Shouldn't be too difficult to do. Again, you can always just go to the very end and choose the strongest base that you can think of, you know, for example, something like this. That'll work to deprotonate anything, a carbanion ion, right? But that's not really the intention. Whoops. That's not really the intention that we have here. We're trying to choose, let's say, the weakest base that's going to accomplish that. That means that we just need to choose a base whose conjugate acid is just above -1.7. If I look on my table here, the next acid would be HNO3. So then do I just put this here? Hopefully you all said no, because that's the acid form or the conjugate acid form, not the base form. So what do I need to do? If this is my acid, how do I get the base, the conjugate base? I'm going to get rid of that proton and put a negative charge on there. So one way to, in terms of the weakest base that I could use to accomplish this, that would be NO3- or the nitrate ion. And then I could replace my conjugate acid with HNO3, which has a pKa of, what was it? Negative 1.3. And so this reaction would indeed proceed in that forward direction. Okay, so just practical considerations of what acid do we choose to protonate a base? What base do we choose to deprotonate an acid? There's one thing that we have to consider when we're choosing the solvent of a particular, for a particular acid-base reaction. 99.9% of the time, we like to use water as a solvent. It's very plentiful, it's cheap, right? Awesome. The problem is that if you're using too strong of an acid in water, all that's going to happen is it's going to protonate the solvent molecules, the water, and not the base that you want to protonate, right? So this is what's called the leveling effect. The bottom line with the leveling effect is if we choose an acid that's stronger than HNO3, than the hydronium ion, H3O+, it can't be used in water. If you try to use it in water, all you're going to do is generate hydronium. Likewise, we cannot use a base that's stronger than the hydroxide ion. If we choose a base that's stronger than the hydroxide ion, all it's going to do is react with the solvent and create hydroxide. Okay, so these are also sort of just solvent effects that you have to consider. If you can't do it in water, you would have to choose something that has a that's harder to deprotonate. There are things called aprotic solvents, acetone, for example. And even then, you always have to consider the pKa of the pKa of the conjugate acid of whatever solvent you're using. Likewise, with a base, you'd have to consider the pKa of the conjugate acid of the base you're using. So then let's also talk about solvation. So this is one sort of added effect that goes on to our REO, or our qualitative understanding of pKa. And so for example, if we're going to compare the pKa's of ethanol and Tert-Butanol, this is something that we actually did in a previous slide, and we saw that ethanol was actually slightly more acidic than Tert-Butanol. Okay, so why is that? That actually has to do with solvation. If we just picture Tert-Butanol, we're going to see this a lot about Tert-Butanol. This big, bulky back end has a lot to do with the chemistry of Tert-Butanol, and in particular, the ability of solvent molecules to solvate that alcohol group, and more importantly, what happens when it gets deprotonated, right? So now we're comparing the conjugate bases of these two molecules here. One of them is going to be stabilized by the fact that the solvent can surround it completely, and that's ethanol, or ethanol's conjugate base, which is the ethoxide ion. Just, you can see by this simple picture here, because the ethoxide ion is less bulky, the solvent molecules are able to surround it even better, stabilizing that charge. Whereas with Tert-Butoxide, the solvent molecules can't quite surround it quite as well because it's got that big bulky group. Okay, so solvation, so right, these, what makes a strong acid? The stability of its conjugate base. This is just one more added factor that might help stabilize a conjugate base, and that's just the ability for the solvent to surround that charge. The last thing that I want to point out is relatively straightforward, and I don't even know that it bears saying, but I think it does, so let's just be clear. We will often write our balanced chemical equations like this, where we're paying attention to what would be the base, reacting with the acid to form the conjugate acid, and the conjugate base. Okay? However, you can never just have, this type of ion all by itself. Like, you can't go to the back stockroom and pull out a whole bottle of what's actually called the amide ion, which is super annoying because that's different from the amide functional group that we learned about. I don't know why they decided to name them the same thing. It's one of those times that chemists are just cruel. But yes, this is the amide ion. You can never just have an ion by itself. It always has to be in the presence of its counter ion. So When you go to the back stockroom and you grab your amide, it's actually counterbalanced by a sodium ion. Sodium and lithium are pretty ubiquitously the most common, okay? But yeah, it's honest. It's one of those things that we get lazy and we omit is there when we're talking about the organic chemistry, the important part of what's going on. And it's just important to remember naked charges don't exist. They're always balanced by a counter ion. So yeah. Same thing with the OH at the end, right? You can't just isolate hydroxide all by itself. It's going to be in the form of sodium hydroxide or something like that.